In this section, we discuss a more general channel model called the band-limited colored Gaussian channel. The schematic diagram for this channel is the same as the schematic diagram for the band-limited white Gaussian channel. The only difference is the noise process, Z of t. Specifically, Z of t is a zero-mean additive colored Gaussian noise, meaning that the power spectral density is not necessarily a constant. X prime of t and Z prime of t are filtered versions of X of t and Z of t respectively, both band-limited to the interval 0W. The output process Y of t is equal to X prime of t plus Z prime of t. And Z prime of t is a band-limited colored Gaussian noise with the power spectral density as Z prime of f greater than or equal to 0 for f from minus W to W and equal to 0 otherwise. As for the case of the white Gaussian channel, we regard X prime of t as the channel input and Z prime of t as the additive noise process. We also impose a power constraint P on the input process X prime of t. Recall that the capacity of the white Gaussian channel band-limited to the interval 0W is equal to W times log of 1 plus P over N0 times W bits per unit time. For the white Gaussian channel band-limited to the interval FL, FH, where FL is the lowest frequency and FH is the highest frequency, and FL is a multiple of the bandwidth of the channel, W, equal to FH minus FL, we can apply the bandpass version of the sampling theorem to obtain the same capacity formula. This model is called the bandpassed white Gaussian channel. When FL, the lowest frequency, is equal to 0, the bandpass white Gaussian channel reduces to the band-limited white Gaussian channel. Here is the filter associated with the bandpass white Gaussian channel. Note that the lowest frequency, FL, is a multiple of W, the bandwidth of the channel. And this is the schematic diagram for the bandpass white Gaussian channel. Before we derive the capacity of the band-limited colored Gaussian channel, let us first recall the assumptions of the channel model. Z of t, the noise process, is a zero-mean additive colored Gaussian noise. X prime of t and Z prime of t are filtered versions of X of t and Y of t, respectively, both band-limited to the interval 0, W. And the input power constraint on the input process X prime of t is equal to P. This is an illustration of the power spectral density of a band-limited colored Gaussian channel. We now derive the capacity of such a channel. First, divide the interval 0, W into k subintervals. The width of each subinterval is delta k equal to W over k. Let the ith subinterval be FLI, FHI for I from 1 up to k. As an approximation, assume that the noise power over the ith subinterval is a constant SZI. Then the channel consists of k subchannels, with the ith subchannel being a bandpass white Gaussian channel occupying the frequency band FLI, FHI. Let Pi be the power allocated to the ith subchannel. Then the capacity of the ith subchannel is delta k times log of 1 plus pi divided by 2 times SZI times delta k. The workout of this expression is as follows. For a white Gaussian channel, which is band limited to the interval FL, FH, where FL is a multiple of the bandwidth W prime equals FH minus FL, with noise level N0 over 2 and power constraint P, the capacity is W prime log of 1 plus P divided by N0 times W prime. For the ith subchannel, W prime is equal to delta K, P is equal to Pi, and N0 over 2 is equal to SZI, or N0 is equal to 2 times SZI. With these, we can obtain the expression in step 5. The noise process Zi prime of T of the ith subchannel is obtained by passing the noise process Z of T through the corresponding ideal bandpass filter band limited to the interval FLI, FHI. It can be shown that the noise processes Zi prime of T, I from 1 up to k, are independent. We will leave this as an exercise. By sampling the subchannels at the Nyquist rate 2 times delta k, where delta k is the bandwidth of each subchannel, the k subchannels can be regarded as a system of parallel Gaussian channels. Thus, the capacity of the channel is equal to the sum of the capacities of the individual subchannels when the power allocation among the k subchannels is optimal. Let Pi star be the optimal power allocation for the ith subchannel. In step 5, we obtained the capacity of the ith subchannel when Pi is the power allocated to that subchannel. Then the capacity of the system of parallel Gaussian channels is equal to summation I from 1 up to k, delta k times log of 1 plus Pi star divided by 2 times SZI times delta k, where the fraction inside the logarithm can be written as Pi star over 2 times delta k divided by SZI. And by proposition 11.23, the values of Pi star over 2 times delta k is equal to the positive part of nu minus SZI, where the water level nu can be obtained from the constraint summation Pi star I from 1 up to k equals P. As k tends to infinity, where k is the number of subintervals, the capacity of the system of parallel Gaussian channels given by this summation tends to the integral from 0 to w log of 1 plus the positive part of nu minus Sz of f divided by Sz of f df. This can be written as 1/2 times the same integral from minus w to w, because Sz of minus f is equal to Sz of f. That is, the power spectral density is symmetrical about f equals 0. On the other hand, as k tends to infinity, summation I Pi star is equal to summation I 2 times delta k times the positive part of nu minus SZI. And this summation tends to 2 times the integral from 0 to w, the positive part of nu minus Sz of f df. Again, this can be written as the integral from minus w to w, the positive part of nu minus Sz of f df, because the power spectral density is symmetrical about F equals 0. Therefore, the constraint summation I pi star equals P tends to the constraint the integral from minus W to W, the positive part of nu minus SC of F dF equals P. So, the capacity of the band-limited colored Gaussian channel is given by this formula, where the water level nu can be obtained by this constraint. The optimal power allocation given in equation 1 has a water filling interpretation given in the next figure. Here, the water filling is for the range from minus W to W, with the total water volume equal to P. And so, the water volume on each side is equal to P over 2.